usually says something. I'm assuming the mic's working. Yeah. So we were talking about how to make you guys move up closer if you don't stop talking. Just one of you, like Gus, like right there. Yeah. That way, when I throw stuff, I can just go like this, and I won't miss. Okay, we're talking about spin coupling, right? And what spin coupling is when you have two protons that are next to each other. They communicate. Their magnetic fields interact, and you end up for one peak, you might get 2 peaks or 3 peaks or 4 peaks. And the pattern is something like this. The pattern goes like if you have a hydrogen with no neighboring hydrogens, then it's a singlet. If you have a hydrogen with 2 neighboring hydrogens, it's going to be, or 1 neighboring hydrogen, it'll be a doublet. And then 2 neighboring hydrogens will be a triplet. And 3 will be a quartet. And beyond that, we usually just say multiply because it's kind of hard to see. Because remember, the total area of the peaks is going to be the same. So 1 hydrogen in this case. But it'll be split into 5 peaks. And then those peaks, the areas under each of the peaks follows the pattern in Pascal's triangle. So remember what we said, this would be like 1. And this is 1, 1. And this is 1, 2 and 1, and this is 1, 3, 3 and 1. So that's from Pascal's triangle. These peaks here are 3 times these peaks on the side. And so these peaks get super tiny. Once you get like a 5 or 7 or 8, you can't read those. Only in rare cases can you actually see them. Okay, so now, coupling constants. This is assuming that the hydrogens are coupling just to 1 hydrogen, and the coupling constant, we call it J. So J, if you remember what I was telling you before, it's in hertz. It's how we usually do that. And the way you get it is you take the ppm, the parts per million, this is the ppm down here, and you multiply it times the resonant frequency of the spectrometer. In ours, it's going to be 60 megahertz. Oh, sorry, that's a 0. 60 megahertz. And then you divide it by 10 to the 6th, basically. Or actually, will that work? No, that'll work like that. It'll come out in megahertz. That's fine. So you'll get the frequency difference between these two, and that's what we call the coupling constant, J. So here's the thing that happens, though, and this is what you got to be careful of. The coupling constants aren't always the same. So like if you have a double bond like this, it turns out because of the anisotropy. Remember we talked, what's the anisotropy? You guys remember? Yes, the circulating magnetic field created by the pi electrons, right? Because of anisotropy, hydrogens that are by themselves, that would look like that. Hydrogens that are across from each other will have one coupling constant, so we'll call that Ja. And the hydrogens that are adjacent to each other would have a different coupling constant. So what ends up happening is this peak first gets split like this, and then it gets split by B again. So when you're looking at a double bond, right, a couple pieces of information will come out. You'll get the coupling constants between the adjacent hydrogens. That's these guys, H and HB. And then you'll also get the coupling constants for the ones that are across the double bond, like this. If it turns out you have one here, you'll notice JC, this coupling constant is usually the weakest. And you'll get a value that's a little bit different than JB. So instead of getting like a simple pattern of just like 1 or 2 or 3, you're going to get like this. Okay? And they would often call this a doublet. They would call this a doublet of doublets, and they'll call this a doublet of doublets. It's splitting. And the way you do this is by creating essentially a tree for the coupling constants, and you can draw out what you expect to see based on coupling constants. To me, the most important thing, just be practical about this, these coupling constants have relatively unique values depending on whether the hydrogens are next to each other, across from each other, or on the same carbon. So if you're looking at the coupling constants on a double bond, you can tell in which positions the hydrogens are relative to the double bond, whether they're the same side, or whether they're cis, or whether they're trans. Okay. And then if you get patterns like this, you kind of know they're everywhere. Right? It's a terminal. It's got all kinds of stuff on it. Okay. So here are some examples of coupling constants. Again, these are in Hertz. Let's see. Typical like alkane ones are 6 to 8. These are 5 to 7. Like on our NMR, these will look the same. But if you're looking at across a double bond, these are 12 to 18. So what that means is the split between the hydrogens will be bigger than it will be for things that aren't on a double bond. Here, these are going to be relatively close. We may not be able to see these on our NMR because the resolution's not good enough to see it. And everything has to be pretty good, perfect about it. And then on a benzene ring, depending on where the second hydrogen is, right, you get different coupling constants. So the ones that are next to each other on a benzene ring, so if you put a hydrogen here, it's going to split more than if you put a hydrogen here. So, and you can measure that distance and tell what the position is on the ring. Now, to be honest with you, when you're doing benzene rings, and we'll do some of these, you're not usually interested in where the hydrogens are. Like when you're starting this stuff, you're really like thinking to yourself, where are all the substituents on the ring? But really the positions of the hydrogens indirectly tell you where the other substituents are. So if you want to know where a chlorine is, you just have to figure out where the other hydrogens are, right? And then you can figure out from that the position on the ring. So to start with, okay, we're going to do this is two problems in one. So without considering coupling, right, and then we'll do it with coupling, how many peaks do you expect to see for each one of these compounds, right? So, well, let's go through this one real quick, and I'll just sort of walk you through it. This is a methyl group, right? And this is a methyl group. They're chemically equivalent to each other. So you should, without coupling, you should just get one peak, right? If you didn't have coupling between the hydrogens. So this would create a peak, and this would create a peak. On an NMR, where you expect, again, this is 0 over here. Yeah, right around 0.9. You'd have a peak that goes like this, right? And then for this one, these are methylene peaks, right? You expect to find a peak around 1.2 to 1.4. And this again is without coupling. That's like this. So this, if this was 2, 1.4 would be around here. You get a peak here, and proportionally, this peak would be smaller than this one by a factor of 3 to 1, right? Because the ratio is 6 to 2, so 3 to 1. So this, in terms of area, this one's 3 times larger. Now, if you have coupling involved, and you're looking at neighbors, right? See, these positions, this position here, 1.4, with the coupling or without the coupling, it doesn't, its position isn't affected, like its average position isn't affected by coupling. So if you were to blow this one up and look at it, and we're going to put 1.4 here, we'll put 0.9 here, they'd still be in the same position, but because the magnetic fields of the protons are interacting with each other, they get split into more peaks. So how many peaks would you expect to see at 0.9? 3, because it's 2 neighbors, right, adjacent to each methyl group. And so you always get one more peak than you have neighboring hydrogens. Okay? They actually call this an N+1 rule. In that, it looks like an exclamation for some reason. Yeah, N+1 rule, because depending on, like, this is 2, right? So this neighbor to this one this guy has these 2 hydrogens neighboring, so it'll be split to 3 peaks. So that'll be a triplet at 0.9. So remember, triplet is the big one in the middle, twice the size of the little ones, like that. Or it's 3 times the size of the middle ones. And then this one will be what? How many neighbors do these guys have? What's that?
Which one?
Like how many neighbors these 2 hydrogens have? Because you want to say, you're saying 1, but that's because you're thinking like it's this one and this one, right?
No, are you talking about on A, like on the A? Or
On B, how many
B,
how many neighbors is how much?
4 total of all hydrogens. It should be 2.
How many hydrogens are here?
3.
How many are here?
6. 3.
3, so 6, right? So it has 6 neighbors. So the n+1 rule says it would be 7 peaks.
So it's just on the side it includes all the hydrogens not have neighboring.
Yeah, all of them. Yep. And part of that's because we're looking at this like it's static, right? But those bonds are actually rotating very fast. And so they basically become homogeneous. They become like one hydrogen neighbor 3 times. I don't know how to explain that, right? But they're basically, the signals from these are homogeneous because the rotational rate is so fast. Okay, so yeah, so this will be, I don't even know how you draw it, but it's an odd number. So I know I'll have a peak in the middle, right? It's going to be big. And then there'll be another peak over here. Another peak over here. And little peaks here like this. And there'll be 7 of them there. It's hard to, you can't see it really, but there'll be 7 peaks over there. So they make it a little more contrast. That doesn't really help. Those windows are too open in the back. Shut these a little bit. Oh, come on now. I had these shut like this the other day, but I think something felt like they were being bothered. You guys, since you're in the back by these windows, you get enough light you can see them. Yeah. Okay, let's do B. Try doing B first with how many different signals would you get and approximately where they would be. And you can go back in your notes because like there's a chlorine here, right? And a chlorine here. So you can kind of guess where it'll be because we earlier like looked at, sorry, went way back. These charts, right? And a chlorine puts it about 3, puts this one about 3 to 4.
What's the
What's that?
no chlorine? I know that's
Yeah, we did a bunch of these. Yeah. Anyways, shifts it about 3 to 4, to about 3 to 4. So adds about 2 to it. Let's go back to this problem. And then we'll do some problems, and then we'll do carbon NMR because you can do carbon NMR as well. All right, so here's a chlorine here and a chlorine here. It's in one of those charts about halfway down.
Halfway down?
Yeah, I'll show you. Yeah. Here, that's a chlorine. 3 to 4. That's just one. And then to have one next to it, I don't know, I guess it's like a half or something. It's not going to be as much as an oxygen next to it because oxygens are way more electronegative. And you have to remember each one of these, right, has a slightly different offset. And just to be real clear, there's not a real like hard answer, like this is the right answer. So we're all going to be around the same places, but we're not going to be exactly right. The only way to get it exactly right is to stick it in the NMR and see where it shows up. Or do a lot of calculations that we're not going to do.
Okay, so for chlorine, they're doing B. Oh, I just did it.
Like that. All right. Where do you think A will be?
0.9.
Yeah, about 0.9. It's got a chlorine on a carbon that's next to it, so it might be closer to 1 or 1.1 or something. It's going to be a little bit off of that, but you would expect a signal in this range here. All right. What about for B? Oh, sorry, for B. Sorry, this one.
0.9 plus whatever chlorine is.
Probably about 2 or so, right? So it'd be 0.9. So say it's 1 and you had 2, so it's going to be around 3. Now it's a CH. It's a methylene group with a chlorine on it. So methylenes are normally around 1.2 to 1.4. So we're going to add 2 to that. And so we'll end up here a little bit to the left of 3. All right? Because CH2 default 1.2 to 1.4. CH3 is about 0.9. Again, the chlorines make it hard to exactly predict where things will be, but that's about where you'd expect it. And then what about this guy here? This one would be the one that's closer to 3 because it starts out at 0.9. It's got chlorine next to it and a chlorine on it, right? So you'd expect another signal around here. Now, in terms of sizes of signals, there's a 2 to 1 to 3, right? So this one would be 3 times. Again, this is for B. This is for this guy here. And then C would be 2. And then B would be 1 like this. So that's how big the signals are in terms of their area. Like if you never did the integration, if you had calculus. Sorry, Adam. Sorry, say that again. That made sense to you though, Adam, right? The whole integration thing, we're just calculating the area underneath. Yeah, well, that'll actually help you when you get to calculus. You're going to do trapezoid rule. You'll be like, why am I doing trapezoid rule? Good. So how many neighbors, so the signal A, oh, let me do this. Starting from right to left, this would be A, all right? This is C, and this is B. That's what we determined. How many signals will you see? What's the multiplicity is what we would say. What's the multiplicity for carbon A? What will that look like?
5.
How many, so how many neighbors are adjacent to it directly? It's not all the neighbors, it's just the one right next to it.
Yeah, the chlorine, it's just H?
Just the H. The chlorine probably won't couple.
Okay, so then
1 plus 1, so you'd be 2 peaks, right? Yeah, so this would really look like a doublet. So I'm just going to draw it like this. And then we're going to make an assumption that when we're doing this, taking into account coupling, that the coupling constants are the same. If they're not the same, we'll talk about that. You'll get something slightly different. What will C look like?
C?
Yeah.
4, 2, 3, 4. That's one neighbor.
One neighbor.
Yeah.
So 1 plus 1, 2, right? That's all you have to do. So this will be a doublet too. Oops, sorry. C will, I can't put my hand on the screen right there. It keeps swaying. So this will be a doublet. And the coupling constants, the J values will be the same. Same split. If the we are assuming coupling constants are the same. And then what does C look like? Or B look like? Sorry, B.
B? 2, so 3.
1, 2, 3, 4, 5.
Shit, 6.
6, yeah? So it'll look like 6. Okay. And so it'll look like this. So if this is where the signal is expected to be, you'll have a peak on either side, and then another peak, and another peak. And then you could, I didn't make it, I didn't start off big enough. Let me start off bigger. It'll look something like this. It'll be 6 peaks like that, and it'll be centered right on where you expect the peak to be. So here's the thing. Not all on our NMR, I don't think we'll see the difference. If we ran this on our NMR, we'd see 6 peaks, or we'd see maybe 4 peaks, and 2 would be buried. But if the coupling constants aren't the same, right? Then what happens is you get something that looks like this. Oh shit! Gosh darn it, stupid thing. Okay, I'll just try to draw it without changing the screen. So the signal, you might expect it to be here, right? Let's say this is on the NMR scale, like where you expect it to be. So this is like parts per million down here. And I'm scribbling all over this slide. We're not going to do all these. We're just going to do a couple of them. So original signal, let's say I thought it was going to be right here. But on one side, this guy's got 2 neighbors, so it's going to be a triplet, right? On the other side, it's got 3 neighbors. So that's going to be a quartet. So what's going to happen, very likely is going to happen, is it's going to split up into a triplet like this. Oh, sorry. Middle one's going to be bigger, and then the side one's like this. And then each one of these could get split into a quartet. So what happens is the signal from this guy gets split to a triplet by this guy, and then each one of those triplets gets split to a quartet. So on the very bottom here, you know what you're going to see? You're going to see stuff that looks like this, because it's going to be a triplet of quartets or a quartet of triplets, one way or the other. It depends on what the coupling constants are. The bigger one decides whether it's going to initially be a triplet or a quartet. And then after that, the smaller one determines like how many peaks there's going to be. So, in each one of those. Yeah, so it gets a little bit complicated. The good news is on our NMR, the resolution's bad enough, you probably wouldn't see all that. You might see some extra peaks down here, but you probably would mostly see, 6 peaks. So we'll go with that for now. So I'm gonna leave the rest of them for you to sort of fiddle with overnight, and on Tuesday, yeah, Tuesday, you know, show me what you got for a couple of them, see how you did. Sure. All right. So we're going to determine the structure. There's chemical formula, and I'm going to walk you through this first one. So you can tell they did this on a really nice NMR, because you see that? You never see that on our instrument, okay? In the middle. You can actually count the peaks. There's 1, 2, 3, 4, 5, 6, 7, 8. That's a lot. Doesn't happen very much. Okay. So what they did is they took these 3 peaks and they blew them up so that you could see them. So this is this one. See, I don't know if you can see it on your printout, but this is around 0.9. This one's around 1.6, and this one's around 2.6. So we have this chemical formula, C9H17, right? And we want to figure out what the structure is. And the first thing that you want to do, we talked about this a little bit last semester when we did IR, we want to do degrees of unsaturation. So what you have to do the degrees of unsaturation is you have to figure out what a saturated compound would look like, and then figure out how many pairs of hydrogens aren't present in this formula, okay? So we're gonna calculate H's for saturated. And then basically we're going to take the difference in hydrogens and divide it by 2, and that's your degrees of unsaturation. Okay. It's not delta H like, you know, enthalpy. It's just a difference in hydrogens. So for C9, for a saturated compound, it's 2N plus 2. So for saturated, it's C9, and what's 2 times 9? 18 plus 2, that would be 20, right? So H20. So this is my saturated. And I use 2N plus 2 to get that formula to get that. So I know how many hydrogens are missing.
Bunch.
Subtract 8. So the difference in hydrogens is equal to 8. So if I take that and divide it by 2, I get 4. So there's 4 degrees of unsaturation. So here's the thing. 4 degrees of unsaturation means a lot of different things. It could mean 4 different double bonds. It could be 4 different rings. And it could be 4 different combinations of those. Like there's more than 4. There's a lot of combinations that give us that. It could mean triple bonds. It could mean all kind of triple bond and a ring. And a double bond. I mean, it could, so anyway, but here's the thing. You see the signal here? What does that mean? Benzene ring. And a benzene ring, oddly enough, has 3 double bonds, and it's a ring because it's a benzene ring. That's 4 degrees of unsaturation. So here's the thing. If all 4 degrees of unsaturation are in the ring, these guys are unsaturated. I mean, they're saturated. Sorry, I said it wrong. If all the degrees of unsaturation are in the ring, then these have to be saturated. Right? Okay, so let's figure this out then. So I have a ring. And that's 6 of my carbons, right? So that would be like, that leaves me with like C3. All right. And what I'm going to do is I'm going to make an initial assumption that there's only one substituent on here. And the reason for that, and I'll tell you why that is in just a second. The reason for that is if there was 2 substituents on here, right, then there would have to be 2 carbons on one side and then maybe 1 carbon on the other side. And this guy would be a singlet because there's no neighboring hydrogen on this carbon. Are you in this class?
No.
Oh. Well, sit down anyways. Have you taken OChem?
No.
You should have come here. You should have come here on Tuesday, and then you would have learned this because this just looks like nothing like OChem. This is just all instrumental analysis stuff. Like a physicist could understand this. So are you a physicist?
No.
Good. There's not enough room in the world. Okay, so yeah, so let me say that again since you distracted us by coming in. What was your name again?
Jose.
Jose what?
Michel.
What?
Michel.
Michele?
Yes.
Okay, well I just recorded that, so now we know.
Awesome.
Yeah. And then I'm streaming this live so somebody may have watched it too. So if the police are looking for you, you should probably like change your name right away. All right, so what I was saying is, okay, if I take 6 of the carbons out of here, that only leaves me 3 carbons. If I have 2 different groups, at least one of them has to be a singlet. If I have 3 different groups, they all have to be singlets. And the reason that is because on this carbon on the ring, there's no hydrogen. There's no neighboring hydrogen. So anything attached directly to the ring on one side never has any hydrogens. And if it's a single carbon, it has to be a singlet. So when I saw that, okay, I decided that all 3 of these must be together because there are no singlets in the compound. Okay. Now, that's a new idea to you, right? It's okay if it's a little confusing. It's gonna happen over and over again with NMR spectroscopy. You're gonna be like, I don't understand that. And then you'll understand it. And then the next time you do it, say, oh, it's that thing, right? I often tell people spectroscopy analysis is like recognizing your dog. Because when you see your dog, all dogs kind of look the same. But when you see specific features of your dog, you're like, oh, that's my dog. I'm like, you kind of know. And when somebody says, how do you know that? What do you say? Because he looks like my dog, right? This is how spectroscopy generally works, is you learn patterns and then you apply these patterns over and over and over again. Okay, so if I assume that all three of these are together, right? There's a bunch of different patterns that they could be in. Okay, so what do we think this guy is?
Well, isn't that one double?
I mean, look, that one's actually a triplet, but where on the spectrum is it? What's its range for its parts per million? It's got to be a methyl group. And it's next to a carbon that has how many hydrogens on it? Because it's a triplet, right? Bordering?
Yeah.
No. Dang it. No respect.
All right.
Yeah. I just anybody who walks it, I just incorporate them into the lecture. It's fine. So this one on the right, this is this. At about 0.9, they screwed up the graph down here. The axis isn't quite right. It's actually closer to 0.9. Over here, it looks like it's closer to 0.8. That's because an artist actually laid this out. I'm not a chemist. So let me ask you a question then. There's 3 peaks here. That's a triplet, right? How many neighboring hydrogens are there?
2.
2. So it needs to be next to a CH2, right? So far on my side chain, this is my CH2 over here. Actually, that's not my CH2. This is my CH2 because it's at 1.4. Right? And then you're looking at this guy here, right? 2.8, I think is what it is. 2.6. It's at 2.6. Actually, not 2.4. It's at 2.6. How many peaks are here? 3, right? So that means it has 2 neighbors, right?
Yeah.
So that's this guy here. And then here is the ring. So what my structure actually looks like is this. You can just redraw the benzene ring if you want. So I have a CH2 next to the ring. And remember, because of anisotropy, it shifts. It usually shifts about 1 to 2 parts per million downfield. And it's a triplet because it's next to the CH2. And on the other side is the benzene ring, and there's no hydrogens there. This guy, he's around where you expect him to be, around 0.9, because he's so far away from the benzene ring, the anisotropy is not that important. And the guy in the middle, right? If I count peaks, 1, 2, 3, 4, 5, 6, 7, 8. Well, it came out a little bit different than what I expected, but there's 2 hydrogens here and there's 5 hydrogens here. Right, so it's a total of, 3 hydrogens there for a total of 5, so it should have 6 peaks in it. So this should have been 6. I got a couple of more, and that may be a coupling constant thing. It could be another.
Why is that? Why is the CH2 so tall?
Why is it so tall? Because it has an extra hydrogen in it.
That's why.
And that's why it's bigger. Now the height, you got to be careful. You got to be careful of the height because it'll lead you into thinking that the height is the area, right? But okay. So let's say you took all my mass, but you put it into a body that was skinny.
Okay.
What would happen to my height? I'd be taller, right? So if I squeeze myself really tight, put really tight pants on, I should be taller, right? Yeah. Yeah, right. That's not how it works. I'm just trying to get you guys ready for middle age. So what happens is if these peaks are really narrow, and even if they were all the same height, same area, If there are really narrow peaks on one of them, it'll just look taller. So you got to be careful. This line, remember, this is the integration line. You'll see how this one is about another third higher than those. That means this line from here to here, when you measure this distance from here to here, let me draw it on the screen. People are watching this, aren't seeing this. When you draw it from here to here, this is 3 parts. This is 2 parts. This is 2 parts. And that also fits in with our sort of analysis of the structure.
What's the peak before 0?
This peak at 0 is actually supposed to be at 0. That's your TMS peak.
Okay.
That's the reference peak. And that's why I'm saying an artist put this together because a chemist would have put that at 0. Yeah. So this is TMS. Great. What the heck happened there? Okay. Okay, we'll do another one. So this benzene ring thing happens to be really useful. I don't think it helps us on this one though. There's not even nearly enough. Okay, so I have, here's a typical, this is like an exam question, okay? It says C3H5O2Cl. Give the formula for the carboxylic acids which give rise to the following spectra using that formula. So it's got to be carboxylic acid, right? So that helps you because you got to know what the functional group looks like. So it's going to be like this. C double bond O, and then O H, and then on this side you're going to have how many more carbons?
2.
2, right? So, and it's essentially a saturated compound. So I'm going to go like this, CH2. If I were to put 2 more carbons, that would be CH3 like this. But one of those hydrogens is replaced by chlorine. Okay, but this is the base structure. So that means there's 2 possible compounds. One is this one. And the other one's this one.
It's higher than 0.9. They got 0.8.
So those are the 2 possibles. Okay. So this is what I do. Look at the way they couple. And these are the actual peaks blown up because their NMR is so fancy that the peaks are super narrow and you can't see them. Ours, they'll be wider. We have a lower resolution NMR, which makes the peaks wider. Oh, but our new one just got purchased. So we're going to have a new, by the end of the semester, I think we're going to have 2 NMRs that both work. All right, so here's the deal. Okay, look at the coupling of the peaks and you tell me which is which, and then you assign carbons to the peaks. And I'm going to do this. I'm going to call this A and B and A and B. I'll give you like a minute. And don't forget, you have integrations you can look at too. Right? So it's not just that; it's a bunch of information. Right? The integration, huge in this. You guys got it? Got an idea?
Yeah, that idea.
Okay, which one is this? Is it the top one or the bottom one?
Oh, that's not the top one.
The top one. Okay. Yeah, it's the top one. Yeah, so that's right. So which peak is A?
To the right?
A is on to the right.
Those are the 2 peaks.
So this one?
Yeah.
It's the
No,
this.
No, that's B.
Okay, so it's this one.
Yeah.
Yeah. Why do you say that now?
I just got confused, but the other one is B because it's a CH3 next
Uh-huh.
to the chlorine, so it moves it over.
Yeah. So that one. So B should be the one to
And
the right.
it's next. It has
So
a,
B is this guy.
Yeah.
Yeah,
A's the other one.
and you can tell that because it's a doublet.
Mhm.
It only has one neighbor. Yeah, so this is B. And this is A. And if you look at the integral, look at the integral. It's 3 times bigger than this. And I actually don't know what this is, it's just junk. So this happens in like real spectra, stuff will show up. It might be from contaminated solvent, it could be, I don't know. Because you notice it's not down here, right? The other thing I wanted to show you is this, offset 2.4 ppm. You'll see this a lot in NMR. Between here and 12.4, there's nothing. So they just cut and paste it on and say how far it moved it. That way you just don't have this giant graph with all this stuff squished on one side. Personally, I would have cut it off at 6 and put it in there. But
Would that matter?
no, but this is the carboxylic acid. Okay. And I'm going to talk a little bit about the sharpness of the peaks too in this one. I like this as a good example. It gives us a lot of different things to look at. Now, if you just look at this one, the integrals are the same, right? And these look the same. So this guy has how many neighbors?
2.
And this guy has
2.
right? So, but which one is this? Is it B, A, or B?
That's that's yeah.
It's B because it has a CL on it, right? This is B, and this is A, right? But okay, I wanted to show you another thing. So you'll notice how sharp this peak is, and this is a carboxylic acid, and how fat this peak is, and this is a carboxylic acid, right? Usually this has to do with hydrogen bonding. If there's a lot of hydrogen bonding going on, the peaks get wide because the part that's hydrogen bonding, right, is the hydrogen on the carboxylic acid. When it hydrogen bonds, it becomes attached to 2 different, like, oxygens. And so it bond weakens, and it turns out that it broadens it out, okay? When the bond is stronger and there's no hydrogen bonding, right, then you end up with a single peak. That's usually sharp. One of the interesting things that happens, because this happens in real spectroscopy, like when you're actually doing this in the lab, if you have water, like traces of water in your sample, a lot of times these carboxylic acid peaks will go away. Because not only do they hydrogen bond, the water makes the hydrogen bonding so strong that it just disappears. It doesn't really disappear, but it gets so wide that it flattens out. Okay. And that has to do with like the tightening the belt thing, right? Okay. You're still like, why are you talking about tightening your belt? Okay, let's do this one. Figure out how many degrees of unsaturation there are in here. And assume that the oxygen doesn't matter for the degrees of saturation. Unsaturation. Just figure it out. Oh, do I actually say how? Oh, I actually wrote it out here. Oh, I meant to delete all this. Sorry.
Oh yeah.
Yeah.
See,
saturated is. I should have said it. You guys are all focused.
That's a 4.
Okay, so how many degrees of unsaturation do we see here?
4.
4, right? Now, when we look at the spectra, what are we going to be looking for?
Rings.
Ring, right?
Benzene.
Benzene, right?
Yeah.
So here's an IR, right? And then here's the NMR, and what do we see here?
Benzene.
Benzene, okay?
So which one is benzene?
Okay, so we're going to go back here. We see a benzene ring.
Okay, 2 benzene.
So what that means is we can automatically subtract 6 hydrogens. Or sorry, 6 carbons. Okay? So that leaves me, right, C8, and you subtract the 6, so you get C2. You have 2 other carbons to deal with. That super simplifies the problem. Now we have an oxygen to deal with, right? So what kind of functional groups or things do you see for oxygen? Well, you're going to see alcohols, ethers, aldehydes, or you could see a ketone, right? That's another possibility. Again, we're going to look at the NMR. And we'll look at the IR. So for IR, do we have an alcohol? Alcohol would be right here.
Yeah.
No alcohol. This is the CH2, right? So right here, for a aldehyde, you'd expect to see a peak over here. And for ketone, you'd expect a giant peak somewhere between like 16 to 1800. You'd expect a really large peak for an aldehyde or ketone or an aldehyde for that matter. And you don't see either one of those things. Well, okay, it's not an aldehyde or ketone, right? It's not an alcohol. So what is it? The options are ether, right? Now in an ether, you'd expect a pretty large peak for a CO bond. You'd expect a pretty large peak right around 1200, and that's what we're seeing right here. So this is a CO, right? There's no C double bond O, no COH. I shouldn't put no because no is a functional group too, but whatever. There's no N, so it can't be no. I don't know that. Maybe it's just a no. I don't know. All right. Yeah, so we're looking at some sort of ether. Here's the other thing that we're looking at. These are singlets, right? So what does that mean? They're not together. If they were together, right? So I'm gonna say these are singlets.
So does that mean they're on the opposite side of the oxygens?
What's that?
Does that mean they're on the opposite side of
They could be on opposite sides of the oxygen, or they could be on different parts of the benzene ring. Okay, so what I'm about to teach you is like one of the dark secrets of like benzene rings. There's two things. One are these little peaks here. These are actually what are called overtones, and they're peaks that are multiples of peaks that are down in here. But oftentimes people will use the pattern of the highs and lows to determine what the structure on the benzene ring is. It's really hard because, let me say that, how do I say this? It's really hard to do that because if you have a ketone, the ketone will swamp these out and you won't see it, right? The ketone will be this large peak that's right here. And because it's so big, a lot of this stuff gets buried and you never see it. Also the overtones, these are overtones also for aromatic rings like benzene. That makes it also hard to see. But the real key thing is this pattern here. And this pattern is only created if you have two groups on a benzene ring on opposite sides of each other, okay? So this is what's called a para pattern. This is what we see for para. Para is 1 and 4. You could also look at, because on a benzene ring, the J values, the coupling constants are different. You could also look at these coupling constants, because sometimes you have multiple substituents. You could look at the coupling constants and figure out the relative positions of everything on the ring. But when you see this, typically people just say, oh, it's a para substitution pattern, a 1 and 4 pattern. So that leaves me with this. Got a benzene ring. All right, I'll fill it in like that because I'm being lazy. The substituents are on opposite sides of each other. And there's 1 carbon on each side. Because if the carbons were adjacent to each other, right, then there would only be 1 substituent. Or they wouldn't be singlets, right? Of course, there's the oxygen that could be in between that would make them singlets, but that, you know, you would only have 1 substituent. In this case, I know based on this pattern that I have 2 substituents. And you notice this integration pattern, this is 2 and 2. That also tells you that it's para substituting because there's 2 hydrogens that are the same as each other. And I'll explain that to you in a second on the structure. And then 2 hydrogens that are the same as each other. And they couple with, they're neighbors. They're coupling with each other. Okay, so what is this going to look? What functional groups will I have here then? I got an oxygen. I don't have an alcohol, right?
No.
So the oxygen has to be next to the ring. And then next to him, I have to have a CH3. And this has to be a CH3 like this. This is what's called a creosol. It's a type of compound. They actually used to use it for preserving wood. I remember having to soak lumber in it and then dig post holes and then dump it in the ground. Termites don't like it apparently. Okay, anyways. Which one do you think this is? If I call this, if I just say A and B, which one's A and which one's B?
But which one? Which is B again?
One next to four.
There's
The
A
big one?
and B. Yeah, which one is this A or B or is this A or B?
Left one is A.
Left one is A?
Yeah.
Because of the oxygen, right?
Yeah.
And it's near a benzene ring, and then god dang it. That one's B. Yeah, that's right. Now here's the thing. Again, having the whole tighten the belt thing. You notice how much taller this peak is than this one. But if you integrate them, they're the same size. Okay. When you take the area, A and B are very different heights, but this peak is narrower than this. And that's why it's taller. Okay, so let me do something real quick. I'm gonna draw some hydrogens here. And these doublets will make sense then. If you draw a line of symmetry on this benzene ring across this way, right, you'll notice that the top hydrogens are the same and the bottom hydrogens are the same. These are closer to the oxygen, so they're probably shifted downfield, and these ones are far away from the oxygen. And in fact, CH3s are known to be electron donating groups. We talked about this last semester, and that causes more shielding. So that's probably what these guys are. I'm not positive, but that's probably what it is. Also, yeah, well, side note. So, how many neighbors does this hydrogen have?
That one right there?
Yeah.
Would it be a 3, 3,
How many hydrogens here?
1, 1,
None.
1?
Benzene ring. Right?
Oh, I forgot.
It's this.
I was thinking of just a regular.
Yeah, you're thinking like cyclohexane, right?
Yeah.
So there's none here. So this hydrogen only has that neighbor. Has one neighbor. What should be split as? 2 peaks, right? There's the 2 peaks. But this one's just like this one. So he's also 2 peaks. And they line up exactly the same place because the molecule has symmetry to it. And B, right, is also each one of these is coupled to one of these. And so you end up getting peaks over here. And it's a doublet. These are doublets, right? Because they only have the one neighbor on the adjacent carbon. And yeah. So anytime you see a pattern, like when you see benzene and it's a single set of peaks and they're all clustered together, that most likely means that there are no substituents other than the one on the ring. But if you see any other patterns, it usually means substituents on the ring. It doesn't always mean that, but usually does. All right. I just left this in here. This is IR spectra stuff. I'm going to skip it. See if there's anything else I want to go over in here. Yeah, this is some of what I was talking about, substitution patterns for 2 substituents on a benzene ring. This is the pattern that you typically see for para-substituents or across the ring. You'll notice these are meta, and you'll see that this is the pattern that you get. And then ortho gives you a slightly different pattern too. When we do our unknowns in the lab, we'll see all of these patterns, and you may actually have to go in and look at the coupling constants on these to figure out what their orientation is relative to each other. Okay? But again, on a benzene ring, the coupling constants are different whether or not they're across the ring or adjacent to each other or 3 away, like this coupling constant from 7.15 to 7.02, that's going to be different coupling constants than all the other positions. Oh, and what's this peak in all of them? It's the methyl group, yeah. There's no integrations on here. I didn't put them on. All right, let's see. Well, that's the answer to the problem, sorry. All right, carbon NMR. So we can do proton NMR and we can do carbon NMR. And there's a lot of like proton NMR, there's a lot of techniques for proton NMR. Carbon NMR, I think there's actually maybe more. More. Okay. So same principles as proton NMR. We just use we look at a different frequency range. So if I remember right, the frequency range for carbon is lower than that of hydrogen. So basically, when you're doing carbon NMR, you know how you have a radio and you want to tune it to a different station, like the old radios where have a knob? You guys know what that is?
Yeah.
Yeah. Right. If you're listening to the hydrogen radio station, right, you're just going to turn the knob to the right. I think it's to the right on the, no, it's to the left on the radio because they did it the right way. Turn to the left on the radio to get to the hydrogen, from the hydrogen station to the carbon station. And all you're doing is listening in a different frequency range. But a lot of the principles are exactly the same. We stimulate and then we listen and we convert the frequencies, right, with the sounds we hear into the frequencies that make them up. And that tells us where the carbon signals are. The shifts are actually a lot larger in terms of parts per million, okay? But the signals are a lot smaller. And the reason for it is this. When I'm looking at a sample like CH4, right? 99% of it plus, right, is H1. There's a lot of NMR active protons. It's just the isotopic composition of the element. There's just a lot of it. Carbon 12 is not NMR. It's not NMR sensitive. It has no spin, okay? But carbon 13 does. So when we're looking at carbon, we can't look at carbon 12, which is like 98.9% of the carbon. We're looking at carbon 13. And that's about 1.1% of all the carbon. So automatically, the signal is 100 times smaller, which is not cool because it makes signals tiny. To see this kind of stuff, you need one of two things. You need pure samples. And when I say pure samples, we often refer to them as neat. Okay. And I kind of think neat. Okay, so if you drink whiskey, I don't know if you guys drink whiskey. Have you ever heard the term neat? I mean, no? People, so I've been to Scotland a couple of times. And of course, you go to distillery tours because there's a lot of cool chemistry there and then they give out free samples. But anyways, there's a lot of cool chemistry there. And when they give you the alcohol, you don't drink it neat. What they do is actually add a little water. Neat just means it's straight out of the bottle. Pure, right? When you're doing carbon 13 NMR, it's nice to have pure samples because that's when the concentration is the highest. That's one thing. The other thing, strong magnets. That helps too. And then there's actually a third thing, right? Lots of averaging. So we're going to do carbon NMR this semester in the lab. The only time we're ever going to do it is when we produce a pretty concentrated sample. And then we can do it. It only takes like 2 or 3 minutes maybe to run it. Okay. But yeah, the signals are a lot smaller because only 1% of the carbon is carbon 13. There are some things that happen. There's some ramifications to this. How big does a compound have to be, right, for it to have, for sure, 1 carbon-13 in it. It has to be like 100 carbons. On the other hand, if it's a 2-carbon compound, right, like ethylene, you have to have 100, you have to have 50 of those molecules before you even get like a good probability of there being 1 carbon-13. Now, that's not exactly how the statistics works, but it's something like that. Go ahead.
That says lots of averaging.
Yeah, lots of averaging, yeah. Which means you just do the same sample over and over and over again, and you add the signals together. That's what it actually means in the NMR. They don't actually, they accumulate, they don't actually average most of the time. But that's the way that makes most sense to us. Yeah, so here's the thing. When we're doing proton NMR, right? Proton NMR, we get coupling, right? Because there's a lot of hydrogens on the compound that are NMR active. In carbon-13 NMR, there's no coupling between the carbons because the probability of having 2 carbon-13s in a compound is like what, 1 part in 10,000. It's really small, okay? Or 10 parts in 10,000. Yeah. Yeah. So basically, because of this, okay, no carbon-carbon coupling. Which kind of makes things really simple because based on whatever functional group it's in, its position tells you what it is, like where it is parts per million. The problem is without the coupling, it's hard to place it, okay? So there's solutions to that, and I'll show you what those are in a second. Whoa, that was not supposed to happen. That was supposed to be a change to slide. So this is known as a decoupled carbon-13 NMR. And here's the reason why they call it decoupled. It turns out the carbons can't couple to each other because there's just not enough of them. But they can couple to these hydrogens because they're all NMR active. Is that me? Was that me that dinged?
No, it was Adam. Sorry for it.
Oh.
Sorry for it.
Golly. No, that's okay. That's okay. No, I only worry about it because, you know, I'm an old mom and she's kind of going through some stuff. And so I got a phone call yesterday in the middle of class to deal with this. So hey, this decoupled. Okay, so which one of these, there's A, C, D, and B. Which one do you think is A? Or let's do the easy thing. Which one do you think is D?
D?
D. Now notice this is parts per million. Right.
This one.
What? Which one?
The left.
Left. Yeah. The furthest one, is that what you said? Yeah, that's what it is. It's this one. This is D. What do you think? Which one do you think is A?
A? The one closest to 0?
Yeah, it is. Same principles from proton NMR. Now the numbers are different, right? But a methyl group is still furthest to the right. Which one do you think is B and which one do you think is C?
D to 20.
Like that. You notice it goes A, B, C, D. Sorry. That's normally how I like you to label your NMR spectra. You just take the peaks and you start at the right, you go A, B, C, and D, and then you label the carbons according to which letter it is. Okay. So that's pretty standard actually. And the oxygen doesn't show up, and none of the the H's, none of those show up. But we base it entirely on position. There's no coupling between the carbons because the chance of having 2 carbons adjacent to each other that are carbon-13 is almost 0 as far as we're concerned. You also notice there's a peak out, the peaks out here.
Yeah.
That's solvent. That's what methylene chloride looks like that, this guy here. And this is TMS. They still use TMS as a reference. But now we're using the carbons on the TMS instead of the hydrogens on the TMS for the signal. But the referencing system still works the same. What else is there? Oh, here's the other really important thing about carbon 13 NMR, which is kind of a bummer. Area is not proportional to signal carbons. So you almost never see any kind of integration signal put on top of the carbon NMR. So it's based entirely on position, right, in the spectrum. So it turns out, though, you can make it so that the carbons couple to the hydrogens, and then you can see the number of hydrogens on each carbon. And this is what a coupled spectrum looks like. All right. So again, A, B, C, and D. I'll just fill that in. And there's different ways to accomplish this coupling. We're going to look at something called depth. It's a different kind of NMR. It's not covered in your textbook, but we do use it in lab all the time when we do carbon NMR. But if you look at A here, this is a quartet, right? How many atoms is it coupled to if it's a quartet? 3, right? So this is A. How many hydrogens are there? 3. This is a quartet. This is B, right? Same thing, right? Quartet. This is C, right? 2 hydrogens on it. A triplet. And then D, which is this one, right, has 1 hydrogen on it. So the coupling, using the coupled information, and the way they do this is actually use the hydrogens as antenna, and they stimulate the hydrogens. That causes, it transfers the energy to the carbon, and the carbon sends the signal out. Okay, it's kind of a neat technique, but yeah, so you can couple them together just basically by using the hydrogens as antenna for picking up the signal, and then instead of listening in the proton range, you listen in the carbon range. And so then you get these spectra that look like this, and there's the solvent again. Right, and does it make sense that this is methylene chloride now?
Yeah.
Right, because it has 2 hydrogens on it. So it's a triplet, yeah? In fact, if you're ever curious about, class is almost over. If you're ever curious about NMR solvents, this is a really, this paper that's over here, is really good. It lists all the solvents and what you'd expect to see if the solvent was in your your sample, and what kind of peaks you expect to see. All right. Anyways, that's it. There's actually one problem here, but we'll skip it and we'll do it next time. And next time we'll come back and we'll start with stuff that actually looks like organic chemistry again. Radical reactions.